Because, I mean, a graphing technique that we like to use is plotting critical points and then sketching a curve to fit those critical points. And once we've got that, we can graph our function. Try again. It's not going to be perfect. We do the best that we can. And I've got a graph of y equals sine x. Okay? So if you're wondering, okay, how am I going to graph y equals sine x? How am I going to remember that graph? Starts at 0, goes to 1, but if you don't remember that, your regular calculator will help you with those first couple points. It'll just get you off the starting pad. Get you going, find those first couple points. Once you find that, it's pretty easy. I'm going to superimpose on that very quickly y equals cosine x. I'm going to put them both in the same graph just so we can see that nature of them. Y equals cosine x. What's the cosine of 0? 1. We start at 1. And at 90, cosine is, or pi over 90 or pi over 2, cosine is 0. Okay, and it's the same pattern. So 1, 0, negative 1, 0, 1, 0, negative 1. Here we are at 1, so we're going to go back to 0, negative 1, 0, 1. So if I can graph my cosine function, it's just a curve like the sine function, just shifted over, isn't it? You put them together, they look kind of cool. Okay? It's essentially the same graph, just shifted over, isn't it? Same graph, just shifted over. So those are my two basic graphs, and that's, again, that's a basic question for tests, quizzes, final exams. Graph y equals sine x, graph y equals cosine x. Know the basic graph. And once we know that graph, then we can start learning stuff about each of those graphs, like its symmetry, things like that. Sine has symmetry in the origin, cosine has symmetry in the y-axis. All those sorts of things. Now, the homework that you did last night. Some of it was graphing, some of it was using cofunctions. Sorry, wrong page. There we go. I don't have my glasses with me, but that's okay. So expressing in terms of the cofunction, I think we did what, 1 through 14 all? So like 1 was cosine of 62. The sine of an angle is the cosine of its complement. So tan 32 went with cotangent of 58. Cosecant, the cofunction would be secant, and the complement of 85 is 5, so secant of 5. Cosine of 14 went to sine of 76 for number 4. 5 was cosecant 63. 6 is cosecant 80. 9 is tangent 37. 7 is that, I'm sorry, and 8 is secant of 48. Are there any questions on the 1 through 8? Yeah. Yeah.
Yeah, I had 2 through 20 even, and 21 through 24, 26 through 30.
Was that right? Oh, I'm sorry. What, for what page?
71.
Okay, I'm sorry. I have other problems circled. They must have changed that assignment over time and done less of it. Sorry, I'm sorry I reduced it from what I used to do. I can give you bigger assignments next time. No? Okay. All right. So 2 through 20 even?
Yeah.
Okay, I used to do 1 through 14 all, and then 16 through 20 even. So, all right. Number 10 should be negative 0.7771. Again, because sine is an sine is an odd function. When I change the value of change the sine SIGN of the angle, I change the sine SIGN of the result. 12 cosine is an even function, so it would be negative 0.4540. So I change the sign of the positive negativeness of the angle. I do not change the positive negativeness of the result. And 14 would be positive 0.8090. Are we okay with those? All right. 16 was 7193, it was just a rotation. 18 again, just as a one period rotation, so it's same value, negative 0.8910. And 20 was again a one period rotation, so negative 0.7431. So those are kind of like questions from last chapter. What happens if you rotate one period? You get the same thing, yeah.
How do you know that those are?
Because in every case you add 360 to get to the new angle.
Oh, okay.
That's a one period shift. 21 and 22 were graphs. And what did I have you doing from that point on? Because obviously I have the wrong problem circled here. Oh, even? Okay. 26 was 0.5878. 28 was 0.25 or 2756. Again, just a cofunction thing again. 30 was negative 0.5446. That was a two-period rotation, so added 720. 32 was a one-period rotation negative, subtract 360, so you get the same value again, 0.5592. And 34 was again a negative one-period rotation. But again, we know from our old circle definitions that one rotation gives us the same angle. Okay, 360-degree shift gives the same value, so negative 0.9511. Any questions on any of that stuff or anything you want to go over further? Yes? 41. Sketch a graph of y equals x and y equals sine x in the same coordinate plane. Find the approximate solutions for x's and radians. All right. Take the cosine graph here. I'll pull that off for the moment. Whoops. Just going to move that. And if I graph y equals x here, now this is a little bit tricky because units are an issue at this point. Because pi over 2 is about 1.7, right? And this is 3.14 or 1.6 something, and this is 3.14. So if 2 blocks is 1 here, and this is about 1.6, 1 is right about here on this axis. And 2 is right about there, and 3 is right about there. So we have to kind of make the axes the same values. So I got to figure out where 1, 2, 3 go on that pi axis that's measured in pi. The blocks aren't exactly one block is exactly the same. It's a little bit off. So that's tough. But when I do that, then I find the 0.11, okay, and the 0.22. And if I graphed y equals x, we'll find, and my graph probably isn't good enough, my sine graph probably is not good enough to actually pick this up. Well, it does in the negative. Okay? In the positive, my sine graph probably should be more up here. But it's picking up that we have the same values at 0, and we have a point of intersection there at root 2 over 2. That one picked up pretty well. But again, that's really a function of my graphing ability more than anything else and the accuracy of the picture. Something like this, we'd probably want to do more on using a graphing utility of some sort to see it. So let's try that with a graphing utility for a second. Let's see it a little bit better. Where is it? Where's my graphing calculator? Congruence theorem is math test. Free graphing. Oh, there it is. So, y equals sine x. Okay, second function, y equals x. And even there, it's a little tough to see, but we can zoom in here. And we see, obviously, that the two intersect at y equals x. And then if we really zoom in, They are almost identical, but we should be seeing a point of intersection right at about root 2 over 2 and negative root 2 over 2. But it gives you an idea of what the graph looks like. And so it is, I mean, I guess maybe my graph wasn't so bad because even using the utility here, it's hard to see those points because of the angle it's at. I should probably cut that problem out next year just because it doesn't really work well from a picture standpoint. I'll make a note of that. But that's what's going on. So I guess my graph probably wasn't as bad as I thought it was. Get the idea. All right. Now if I put cosine back on there. Cosine. Okay. Cosine y equals x, we get this. We do get a point of intersection up here, but that's the only one. Other questions? Yes, sir.
Can you go over like number 12, why it's negative or positive?
Okay. Tell me again what the problem was for number 12. Save me a second if you haven't go look at it. You're given what?
If cosine is 117 degrees.
Cosine of 117 equals
Negative 0.45.
45, I'm sorry, 40, and it wants us to find the cosine of,
Negative 117.
okay. Now remember, cosine is, let's look back at our graph for a second. Cosine is an odd function, right? I'm going to take y equals x off here for now. I don't want that. That's confusing me. Okay. In fact, let me just do this. Oh, it's doing that. Okay, never mind. It's okay. We're going to make this work. That's fine. Okay. Just trying to get rid of some of this excess stuff. I'm sorry. I'm just going to put cosine up here for a second. All right, I'm going to take sine, get rid of that. And just bring cosine in. Okay. Notice that cosine symmetry is with the y-axis, right? So if I have the cosine of an angle like 117, that'd be like over here somewhere, right? 0.454. That'd be 117 over and down. Here, we do have symmetry in the y-axis. So if I go the same distance out there, is my y value going to be opposite or the same when I go either way? It's going to be the same, right? That's the symmetry in the y-axis. That's the cosine of negative x equals the cosine of x. So that's why when we switched from cosine negative 117, cosine 117 equals 0.4540. That's why cosine of negative 117 would have to have the same value, actually, negative. I remember it's negative because I know 117's out here, it's negative out there. Okay, but we can see with the graph it helps us understand that symmetry a little bit better. And again, that's why I think the graph is really powerful in knowing it, because if you can quick sketch that graph, a lot of times you can see that symmetry. You don't have to memorize the symmetry if you can see that through the picture. Does that help? Okay. Does that make sense to other people? Yeah. Honestly, I don't remember. I'll be honest with you, I do not remember all the symmetry rules. When I have to figure them out, I just do a quick sketch of the graph. Oh, then I can see the symmetry. I don't have to remember it. I can see it in the picture. And for my learning style, seeing that picture tells me everything I need to know. For other people, memorizing the formula is a much better way to go. So we got choices. All right? Other questions? Now that we've got the graph of sine and cosine, let's play with them. Let's manipulate them. Let's change them up. Like going, great, I just learned what the graph is, now you're going to change it. Reinforce it again. Graph of y equals sine x. Very quickly. Starts at 0, then 1, then 0, then negative 1, then 0, then 1, then 0. Okay, then negative 1, 0, 1, 0. Okay? There's a basic graph. Y equals sine x. Now, what if I said y equals sine... Oh, did I do that one first? Sorry. I want to do this one first. Same start with y equals sine x. There are two different manipulations we're going to learn today. You're going to see me do this graph this way 100 times. Hopefully you kind of get the idea, at least through sheer repetition, that this is the way, a good way to make the graph. What if I did y equals 2 sine x? What that's going to do by multiplying the 2 in front is we're going to just multiply the y value by 2, whatever we get. So 2 times 0 is 0. I'm not going to multiply all my values because I know the general shape. I just need to multiply the ones that are critical, the zeros and the ones. So instead of going from 0 to 1, it's going to go from 0 to 2. And then back to 0, then down to negative 2. Then back to 0, then to 2, then to 0. So negative 2, 0, 2, 0. Okay? The purple there is y equals 2 sine x. Do we change the period of the function at all? No, we don't change the period. When we multiply a number in front, we're changing what's called the amplitude of the function. Amplitude is a measure of deviation from 0. Waves have something called amplitude. How tall are they? That might be an easier way of saying it. Deviation from 0 is kind of a mathy way of saying it. In the common way of speaking, we might say, how tall is the wave? That's amplitude. And so that's one thing we can very easily manipulate with a sine or a cosine function, with a wave. How tall is it? If I put a 2 in front of here, instead of going to 1, it goes to 2. If I put a 5 in front of here, it would go up to 5 and down to negative 5. We can adjust the steepness of that. Now, that's called amplitude manipulation. Or you use something sometimes in your car that changes amplitude all the time. It's called a radio. And sometimes, if your parents are driving probably, they might listen to AM radio. AM stands for amplitude modulation. That's an example of changing amplitude. What you're seeing in AM radio is they change the amplitude of the radio wave that's being sent through the air. And by broadcasting at a particular amplitude and you turning your receiver to receive that amplitude of wave, you receive different stations. The waves all have exactly the same frequency, they just have different amplitudes. That's what AM radio does. It's amplitude modulation of the wave, of the radio wave. They're all being broadcast at the same frequency, just with different amplitudes. And your receiver tunes in to different amplitudes. That's what's going on. Okay? So amplitude is changing the height of the wave. The other thing we can change is, or another thing we can change is the frequency of the wave. What if I have a graph of y equals sine 2 theta? So instead of 2 being out front here, now the 2 is multiplying theta. What's that going to do? Well, let me just tell you. Let me show you, and then we'll explain the formula behind it in just a second. When I put the 2 inside, what that means is instead of completing 1 period in 2 pi units, it's going to complete 2 periods in 2 pi units. If I put a 5 in there, it would complete 5 periods in 2 pi units. So instead of getting 1 full wave in 2 pi, we're going to get 1 full wave in pi. Not changing the amplitude, the period. And we're going to do it again. So in what was 1 period of my function, okay, from 0 to 2 pi was 1 period. Now in my new function, the same distance gives me 2 periods. We're changing the period of the function when I multiply theta by a constant. And if I multiply theta by a constant less than 1, we stretch it out. Either pushes the waves closer together or stretches them out. The higher the number, the closer it's pushing the waves together. If I use a fraction like 1/4 or 1/3, it's really stretching them out. We're getting along. This tells me, this coefficient on theta tells me how many periods we complete in 2 pi units. We can do this with sine or cosine. And these are our first 2 basic manipulations of the function. Stretching it with amplitude, compressing it or expanding its period by multiplying theta by a constant. So those are 2 basic manipulations we can do. Let's take a look at it from a formula standpoint. Let's just kind of break it down for us. I now have not just y equals sine theta, but y equals a sine b theta. A is a constant we multiply in front, b is a constant that we put in with theta. When I see an equation in that format, the amplitude is a. Whatever that number is, that's the amplitude. That's how high up and down it goes, from 0. The period, there's 2 ways of interpreting B. I could say it completes B periods in 2 pi units, or what I think is a little bit easier is say the period of the function becomes, instead of 2 pi, is 2 pi divided by B, whatever B is. So in our previous example, I said B was 2, so the period would be 2 pi divided by 2, or pi. So it's going to complete a cycle in pi units instead of in 2 pi units. Some of the basic questions we're going to ask with this. We'll give you the function. You don't have to necessarily graph it. Just tell me what's happening. If I have the function y equals 3 cosine 4 theta, the amplitude is going to be what? 3. And the period is going to be 2 pi over what? 4, which I could then reduce as pi over 2. So there's my amplitude and my period of that function. Some of the problems today, that's all you're doing. You're just identifying what is the amplitude, what is the period, given this modification. Let's do another 4. Just stating the period and the amplitude based on the information we're given. Not graphing it yet, just stating the period and amplitude. What would be the amplitude here? Period. 2 pi over 4, which would be pi over 2. How about here? The amplitude would be 1/2, so it's not going up all the way to 1. It's only going to 1/2. And my period is 2 pi over 2, which would just be pi. Here, my amplitude is -2. What would a -2 amplitude do? It'd flip it in the x-axis. It'd reflect it in the axis, wouldn't it? So instead of going from 0 to 1, we go from 0 to -1, and then 0 to 2. The 0 doesn't flip because the negative times 0 is just 0. But wherever it would have been positive, we flip it down to negative, and negative we flip down to positive. So instead of starting to go up and down, it's going to start out down and then up. And it's going to go down how far? 2. Okay? The period is 2 pi over 1/2, because x divided by 2, which would be 4 pi. So this one goes the opposite way and is way stretched out. All right, let's make sure electronics are put away and that people are staying awake here. All right. How about here? Amplitude would be, period is 2 pi over 3. Okay. Now, the amplitude thing most people find really easy to work with. I mean, really? You're just going up to 5 or down to -5, whatever you're doing. The period thing can be a little bit trickier when we're graphing. So if we get something like that, what we're going to do is I'm going to teach you a technique that is way easier than what the book has you do. It requires you to make a sketch first and then transfer that information over to your graph. So first we identify what is my period and my amplitude. My amplitude period here would be 2 pi over 2, or just pi. My amplitude would be 3. Now, I know it's a sine function. It's got a positive amplitude. If it had negative amplitude, I'd have to flip it. So I know my basic shape of my graph is like this. So I start with just a basic graph, no units on it. I just start with my basic sine curve. No units anywhere. And now what I'm going to do on my sketch is I'm going to identify what my units are. My amplitude is 3, so I know my maximum here is at positive 3, and my minimum here is at negative 3, and I know, of course, that that's 0. I'm not putting it on graph paper yet. This is a sketch. This is just a working, just a working drawing that I can manipulate and doesn't have to be to scale or anything like that. What I say the period is, I've graphed one period of sine on purpose. In this case, a period is how far? Pi. So I know that this point is at pi on the x-axis. This point here for sine is halfway. So what is halfway between 0 and pi? Pi over 2. Now we want to get the critical points. We want to get the maxes and the mins. So I want this point, which is halfway between 0 and pi over 2, which would be pi over 4. And this point would have to be, so it's 1/4, 1/2, 3/4, 3 pi over 4, and 1. Aha. So what I've done is I've identified in a sketch these 5 critical points for a period and where they are located. And now when I do my actual graph, I just transfer this information to an actual graph. So I say, okay, y equals 3 sine 2x between 0 and 2 pi. I know I start at 0, 0. Plot that point. At pi over 4, I'm at 3. Well, pi over 4 I know is right about halfway here. I'm at 3. At pi over 2, I'm back at 0. At 3 pi over 4, I'm at negative 3. And at pi, I'm back at 0. So there is the actual graph of what that function looks like. Now, it did say between 0 and 2 pi, so now I have to just continue filling that in with my pattern. It's over pi over 4, up, over 1.5 boxes, down, over 1.5 boxes. Now we can just follow that pattern, over 1.5 boxes, up 6, over 1.5 boxes, down 6, 1.5 boxes, or down 6, over 1.5, and then back. So there it is. By doing a sketch first, we don't have to worry so much about, okay, how many periods am I fitting in here and what's the stretch and stuff like that. The sketch really is going to help you get all that sorted out before you actually put it on graph paper. You're going to sort everything out in the sketch first. And then we're going to put it on graph paper. And we can get our graph very quickly. Now, the sketch always looks the same. The sketch is always going to look the same for sine. The actual graphs are going to vary wildly. Some will be pushed together like that and tall. Some will be stretched out and really long. They're going to vary a whole lot based on the information we get from the sketch. And again, why do we care? Because, again, waves are everywhere. Electromagnetic spectrum is used constantly. The reason your cell phones work, the reason Wi-Fi works, the reason all that stuff works is all because of waves. The reason you can see, hear, all because of waves. That's all waves. And we can talk about wavelength, which is the length of for one period. That's what we call a wavelength. Long wavelengths are low frequency, have low energy waves. Short wavelengths, high frequency, high energy waves. Microwaves, very short wavelength, very high frequency. What does a microwave do? It heats things up. It excites atoms and molecules because of a really short wavelength. Extremely low frequency wavelengths travel through water well. They communicate with submarines that way. You've got that ELF transmitter up in northern Wisconsin, extremely low frequency. That's what it stands for, ELF. All right? So this is all stuff that gets used everywhere. Understanding how to manipulate these functions is important. I just want to do one more example before we quit, okay? Just do the sketch part of y equals 1/2 cosine of 3 theta. We're not going to do the full graph. I just want to do the sketch. Start with a basic cosine graph, which I know looks something like this. This is why memorizing the basic graphs is so very important. That's my basic cosine graph. I know my amplitude is going to be 1/2. What's my period going to be? 2 pi over 3. So 1 period, amplitude, that's easy, that's 1/2. And it's going to be negative 1/2. And zero's there. My period is going to be 2 pi over 3. Half a period is right there. So half of 2 pi over 3. And here's where it gets tricky for people. Half of 2 pi over 3. Oh my gosh, what are we going to do? 1/2 times 2 pi over 3 is 2 pi over 6, which is pi over 3. Okay. That's half of the period. This is half of the half. What's half of pi over 3? Pi over 6. Now here's where it gets a little tricky. What's this one going to be? What's halfway between pi over 3 and 2 pi over 3? Well, that would be 2 pi over 6 and 4 pi over 6, right? What's between 2 pi over 6 and 4 pi over 6? That would be 3 pi over 6, which is pi over 2. And again, now I could transfer those points to a piece of graph paper and get a picture of what that graph looks like. It's going to be short, but it's going to be a pretty quick turnaround, isn't it? And once I've got my pattern on my regular graph, that's easy to repeat. But again, why it's so important to know your basic functions. That's a lot of what you're doing today. You won't be graphing every one of them. Realize that. A lot of them you're just identifying what's the amplitude, what's the period. But some of them you're going to be having to graph. Okay? Stick with it. Once we learn this technique, we're just going to keep repeating it, repeating it, repeating it. Let me